Great. Well, I'm happy to be here remotely. Sorry, I'm not there in the room. Fortunately, though, Rachel, Angela, and Jessica, three of my co-authors, are there at the conference. So feel free to tag them this later today if you want to talk to somebody in person about this. So this project, our goal is to try to figure out the source of the hydration features in MCube data. And this is, of course, a ginormous question and problem. And we've heard some excellent talks so far today addressing this issue. Our approach has been focused on the MCube data. And we've been looking at sort of four ways to approach this. The first is comparing targeted and global images of certain locations. And then also looking at the global data that's been processed with a method developed by Christian Wohler and his graduate student Kai Wolfarth recently. And that is using Diviner, Mertis, and Gelfand for data from those missions. Another technique we're using is modeling these spectra and looking at the residual in order to look for changes with the time of day. And also fourth tack is sort of looking at lab spectra to try to compare those with these MCube data. So first off, looking at the targeted versus global images, there are not very many targeted MCubed images. And here is sort of a map in the upper right. And the image we looked at is in this yellow box. And that is processed with the initial Roger Clark thermal correction, and that's available on the PDS. And then we're comparing that with global MCube data. And this image and the lower right with the yellow box shows where that is in the global data set, and the yellow box shows the sort of snap out that we use to analyze this. And one advantage of the global data is that you have broad coverage and you have data from different times of day. And so, for example, the early morning, late morning, and midday have different integrated band depths across the 2.7 to 3 micron region that could be related to OH or H2O, as we heard in the previous talks. And across this highlands region on the far right, lower right, is sort of a mineral map. And most of this image is blue, corresponding to plagioclase. There's a little bit of OPX and a tiny amount of basalt in red. So, and the global data set that we're using here is processed with a thermal correction that involves calibration with LRO diviner data that Gelfand 4 and the Bepi Colombo Mertis missions. And we're really excited that the near infrared and thermal infrared data show high accuracy with these other missions and with the technique we're using. So that gives us high confidence for the technique. So here on the left, we have the targeted mission, targeted image, and on the right, the global image. And these little spots, Angela and Rachel collected these spectra. So there's a pink, green, red, green, pink, and blue spots from both sides. And so if we look at the spectra here, the targeted data, of course, has higher spectral and spatial resolution. So it's smoother. And it's in general very similar to the global data, which is exciting for us. However, there are some issues with binning from the global data that present some challenges. So if we look at the spectra here, on the top are the global data and on the bottom are the targeted data. And generally in these two examples, the red and the green and the pink show stronger pyroxene absorptions, and the blue shows weaker pyroxene absorptions, and that's pretty consistent. The big difference is out at longer wavelengths in the 2.7 to 3 micron region. This new thermal correction is better consistent with other missions, and it shows this change in the 2.7 to 3 micron region that's integrated in this integrated band depths used by Wohler and Wolfarth for mapping water OH on the moon. And so transitioning to this map here, this is from Kai's recent paper in Astronomy and Astrophysics. So if you look at global maps from the morning, to midday to afternoon, we see a higher abundance of this band depth due to water or OH earlier in the day, a reduction towards midday, and then higher again in the afternoon. So something is causing a decrease in this band at midday across most of the moon. And so we looked at some spectra from 3 different strips from these to try to look at the spectral shape and changes in more detail. And these are some examples. So from one of these strips at 240 to 250 longitude, these on the bottom with the triangles, these are the morning data at a few different latitudes. The first step was to normalize these at channel 70. And we did this for the morning and the midday data. And then we ratioed the morning to the midday data. And you can see it's a little noisy in some areas, but it's fairly consistent, except at the end, there's a change in this 2.7 to 3 micron region. And then if we also look at, this is the same plot from before the morning to midday versus to morning to afternoon. In many places, this remains fairly flat from morning to afternoon, and in some places there's some diversion from that. So in the blue and the light green here. And again, if we compare this from 3 different locations, we see the biggest difference from morning to midday, and we see different shapes here from 2.7 to 2.95 or so. And unfortunately, the data is binned and the spectral resolution isn't super high, but we do see differences in the shape near 2.7 to 2.8, which is more associated with OH, versus longer from 2.8 to 3 microns or so, which is more associated with water molecules. So potentially this could be due to different components. So the next tack we applied was looking to model these data. And so we compared midday to morning or morning to afternoon. And in these cases, the original spectra are shown in blue and red. So the blue and the red you can see here, and then the modeled spectrum is shown in yellow. And so the difference between red and yellow is this linear line shown in purple, and then the residual shown in green. So red multiplied by the line gives you the yellow modeled spectrum. And then the residual is pretty flat across here, but there's a difference here in the water area. So for this model, we're looking at what the shape of this residual is and what the intensity of the residual is for different sites on the moon. So for this particular site at Borealis Crater, we looked at midday to morning, and we looked at the change in this region that appears in this residual, and that's shown here. And then Mario Prente was leading this effort, and then he mapped this on the right. And then he did the same thing for the morning to afternoon, and then mapped this on the right. So there is some change in residual, but it's less. So if we compare the map of morning to midday on the left and morning to afternoon on the right, the higher integrated band depth is shown here in red. So there's more orange and red for the morning to midday, and there's still some green showing some increased change in the morning to afternoon. But the biggest change is observed in the morning to midday transition, as observed in the maps that Kai and Christian were working on. So wrapping this up, the last tack is comparing this to lab spectra. And I looked through a lot of my spectra from anhydrous minerals and volcanic glass, and also some from the USGS library. And many of these do have bands at longer wavelengths. And from 2.65 out to 3.2 microns, in these nominally anhydrous minerals, we do see bands due to OH in water. And these could be due to inclusions with trapped water or due to some abnormalities in the mineral structure. And we also heard a lot of lab experiments in the last 2 talks about causes for OH in water in olivine or other minerals. One thing we did note was a change in volcanic glass and quartz and olivine fine-grained components of these tended to have a broad distribution of water, like in this green here or the gray at longer wavelengths, whereas coarser grained olivine and many pyroxene and feldspar minerals tended to have both OH bands as well as water bands. So wrapping this up in conclusion, then we're looking at the MCube global data set, and it's known to show diurnal differences in this 2.7 to 3 micron region, which is associated with hydration. And we see the biggest changes from morning to midday. And using ratios of the spectra allows you to get rid of some of the artifacts from the binning. Using a modeling technique, we saw similar changes where we saw the largest change in this band from morning to midday. And then in looking at lab spectra, perhaps molecular water is embedded in some of the regolith, or OH groups could be protonated along grain surfaces, and potentially these could be involved in differences in this hydration band. So thank you, appreciate the chance to speak today.